My dear friends, colleagues, and students, so today I am going to give a lecture on isomerism and types of organic reactions. So, all the living things they are made of from the carbon atoms, and carbon is having unique property to form a long chain of compounds, and the structure of the carbon atom is a tetrahedral. So, the bond angle between the carbon carbon bond is 109.28, and the unique property of the carbon to form a long chain of compounds, and all the living things are made up from the carbon compounds. So, the carbon compounds also exhibit the isomerisms in the organic compounds. So, what is the isomerism? It is the phenomenon of exhibiting two or more compounds with same molecular formula but different physical and chemical properties. So, the compounds they have the same molecular formula, but they have different physical and chemical properties. So, the compounds which are showing the isomerism, they are known as the isomers. Isomers are the compounds showing different physical and chemical properties but same molecular formula. The isomerism in the organic compounds can be classified broadly into two, that is structural isomerism and stereoisomerism. And the isomerism is due to the tetrahedral geometry of the carbon atom. So, the bond angle between the carbon carbon is the bond angle between the carbon carbon bond is 109.28. So, first we are going to take about structural isomerism. The structural isomerism or constitutional isomerism arises when atoms within a molecule are arranged in different orders. The structural isomers have the same molecular formula but different structure formulae. The structural isomers usually show different physical and chemical properties. The structural isomerism arises when atoms within a molecules are arranged in different orders. So, we are going to show the structural isomerism in the coming slides. The structure isomerism is further divided into these categories: number chain isomerism, positional isomerism, functional isomerism, metamerism, tautomerism. So, when discussing the chain isomerism arises due to different arrangements of carbon atoms leading to linear and branched chain. The chain isomers have same molecular formula but different types of chains. They are either linear or they may be a branched. The different compounds sometimes they have the same molecular formula, but the compounds may be linear or the compounds may be branched. The chain isomers have almost similar chemical properties but different physical properties. For example, the branched chain isomers have lower boiling points than that of their linear counterparts. That is due to the van der Waals forces of attraction. So, the branched chain isomers have least van der Waals forces of attraction, while the linears have more chances to have van der Waals forces of attraction. The linear ones have more surface area of contact and hence the intermolecular forces of attraction are maximum. So it is an example of butane. So linear, it is known as linear normal butane. So normal butane has molecular formula C4H12, while the another isomer of this normal butane is branched one, which is shown in the next. So that is also known as isobutane, and the IUPAC name of this compound is 2-methyl propane. So 2-methyl propane is having low boiling point as compared to butane, because butane is having more surface area as compared to 2-methyl propane. So this is the example of the branched, this is the example of the chain isomer. The next is the positional isomerism. The positional isomerism arises due to the different positions of side chains, substituents, functional groups, double bonds, triple bonds on the parent chain. So the position of the functional group, that is different in isomers. For example, this is the example of the propyl chloride. So here in normal propane, one hydrogen is replaced by the chlorine, and the methyl group, which is at the number 1 position, the hydrogen from this propane is replaced with chlorine. So the IUPAC name of this compound is 1-chloropropane, while now the position of chlorine is here 1. When chlorine is attached to the center of the propane, then it is having name 2-chloropropane. So these type of isomerism is known as positional isomerism. Propyl chloride and isopropyl chloride are the positional isomers with the molecular formula C3H7Cl. These isomers arise due to difference in the position of the chloro group on the main chain. So this is the another example in case of butene. In the following positional isomers, two type of isomers are formed. One is known as 1-butene and another isomer is known as 2-butene, and it is due to the position of the double bond is different in both the compounds, but both these compounds, they have the same molecular formula, and little bit they have same chemical properties, but sometimes they have a little bit different physical properties. So this is the example of the position isomerism. The position of the functional group is different in the linear chain of the butane. The functional group OH is at different position in on the main chain of the following alcohols. The formula is propanol. So this is example of one normal propanol and another is isopropyl alcohol or 2-propanol. The functional group OH is at different positions on the main chain of the following alcohols, and the molecular formula is the same, but position of the OH group in both these compounds are different. In the following positional isomerism, example of the positional isomerisms, orthoxylene, metaxylene and paraxylene. The relative position of the methyl groups on the benzene ring are different. In 1,2-dimethyl benzene, the methyl groups are attached adjacent to the carbon bonds, while in 1,3-dimethyl benzenes there is a gap of one carbon atom of two methyl groups attached to the benzene ring, while in the paraxylene both the methyl groups are attached to the carbon atom far away from each other. So, again these compounds have different physical properties, but chemical properties are almost same. So, next example of isomerism is the functional isomerism. The functional isomerism arises due to the presence of different functional groups. The functional isomers have the same molecular formula but possesses different functional groups. So, in the earlier slide we have told that the position of the functional group is different, but here the functional isomers have the same molecular formula, but they possess different functional groups. The functional isomers show different physical as well as chemical properties. In the earlier example of the chain isomers and the position isomers, they have the same almost same chemical properties, but little bit different physical properties. But in the case of functional isomers, they show different physical as well as chemical properties, because the functional groups are totally different. So, taking the example of the functional isomerism, so the dimethyl ether and ethyl alcohol, they have the same molecular formula, that is C2H6O. So, the composition of the ethyl alcohol and the dimethyl ether is the same, but the functional group in the ethyl alcohol is OH, while in the case of dimethyl ether the functional group is OCH3. So, ethyl alcohol is liquid, while this dimethyl ether, it is a gas. So, they have total opposite properties, chemical and as well as physical properties are different from each other. Similarly, acetaldehyde is a functional isomer of acetone. So, both of these compounds, they have the molecular formula C3H6O. So, acetaldehyde, it has IUPAC name propanol, while the other acetone, that is having the IUPAC name propanone. So, both of these compounds have the same molecular formula, but they have different function group. Acetaldehyde is having CHO as a functional group, while acetone is having C double bond O functional group. So, in the case of acetaldehyde, it is a liquid, while this acetone, it is a low boiling point liquid. So, it gets evaporated very easily. So, both of these compound acetaldehyde and acetones, they have the different properties from physical and chemical properties from each other. This is the another example of the molecular formula C2H4O2. So, this molecular formula shows two type of compounds. Number one is acetic acid, another one is methyl format. Acetic acid is liquid while methyl format is a gas. Both acetic acid and methyl format are also functional isomers. They have the same molecular formula C2H4O2. Acetic acid is a carboxylic acid with the CO2H group, whereas methyl format is an ester with C double bond OOCH3. So, next type of isomerism is metamerism. The metamerism arises when different alkyl groups are attached to the same functional group. Now, in this case, the functional group is the same, but there is a different position of the alkyl groups on either side of the functional group. Now, by taking the example of diethyl ether, methyl propyl ether or isopropyl methyl ether, all these compounds are having the molecular formula C4H10O. So, the molecular formula is C4H10O. So, the molecular formula is same, but there are different type of groups attached around the functional group. So, in the diethyl ether, the oxygen is in the center of the chain, while in case of 1-methoxypropane, this is again example of ether, but at one end of the oxygen there is only one methyl group, while on the other side of the chain there is propyl group. So, similarly, in the case of 2-methoxypropane, the OCH3 group is attached to the center of the carbon atom. So, it is also having common name isopropyl methyl ether. So, this is the example of metamerism. So, the functional group is same, but there is the arrangement of the alkyl group is different on the side of the functional group. So, this is example of metamerism shown in the amines: diethylamine, methylpropylamine or isopropyl In this case, the NH group is present in the center of the chain, and this compound is also known as N-ethyl ethanamine, while the second one compound, that is having N-methyl propane 1-amine. The IUPAC name of the third compound is N-methyl propane 2-amine. So, all these compounds, they have the same molecular formula C4H11 and N, C4H11N, but three type of compounds are formed. So, number 1 is known as diethylamine, second one is methylpropylamine, and third one is isopropylmethylamine. So, same, the functional group is same, they have the same almost chemical properties, but physical properties are different from each other. Tautomerism. Tautomerism refers to the dynamic equilibrium between two compounds with the same molecular formula. It is also called as desmotropism or cryptotropism or prototropy or allotropism. It is most often a special case of functional group isomerism. In general, the tautomers have different functional groups and exist in dynamic equilibrium with each other due to rapid interconversion from one form to another. It is very important to note that the tautomers are not the resonance structure of the same compound. So, in resonance, when one compound cannot show the property of a molecule, but it has contributing structure, that is known as resonance. But it is very important to note that the tautomers are not the resonance structures of the same compound. So, resonance is a little bit different. So, by considering the keto-enol tautomerism, the carbonyl compounds containing at least one alpha hydrogen atom exhibit keto-enol tautomerism. The carbonyl group can be converted to enol form due to transfer of one of the alpha hydrogen onto the oxygen atom. An alcoholic group on C double bond C is called enol, that is an alkene alcohol. The percentage composition of keto-enol tautomeric mixture depends on the relative stabilities of these two forms. In general, the keto form is the low energy form and is more stable than the enol form. However, the enol form is also stable in certain cases due to other stability factors. The dynamic equilibrium between a keto formed due to the complete transfer of hydrogen. However, the relatively stable keto forms exist in the higher percentage. So, the first acetone keto form, it is more stable, while propionyl 2-ol, so it is less stable as compared to acetone. The percentage composition of enol form is less, while the percentage composition of the acetone is more. However, enol form is also appreciably stable in case of 1,3-dicarbonyl compounds like acetoacetic ester or ethyl acetoacetic ester as depicted below. So, here keto form is 92.4%, while enol form it is have little bit contribution, and the contribution is 7.6%. So, this is example of keto-enol tautomerism in acetoacetic esters. The enol form is more stable than the keto form in the case of phenols due to the resonance stabilization of the aromatic ring. So, enol in the case of phenol, enol form is more contributing as compared to less keto form, that is known as cyclohexanone. So, aceto or keto form is less stable in the case of the phenol. The percentage composition of phenol is more and keto form is less. So, that are the examples of the structural isomerism. Now, coming to the stereo isomerism, as I have already told you that carbon is having tetrahedral arrangement or tetrahedral geometry. The isomerism which arises due to different spatial arrangements of atoms or groups is called stereoisomerism. It is broadly divided into two, that is geometrical isomerism and optical isomerism or conformational isomerism. The stereo isomers have same structure formula. So, basically the isomers are known that they have the same molecular formula, but there is little bit different arrangement of the groups on the carbon atom. But in the case of stereoisomers, they have the same structure formula, same connectivity order between atoms. However, the atoms or groups are arranged differently in space. So, there is arrangement of atoms or groups on the carbon atom which is under consideration. So, the groups they are arranged differently in shape. Geometrical isomerism. The geometrical isomerism arises when atoms or groups are arranged differently in space due to restricted rotation of a bond or bonds in a molecule. So, in geometrical isomerism, so there should be double or triple bonds are present. The geometrical isomerism arises when atoms or groups are arranged differently in space due to restricted rotation. Due to the presence of double bond or triple bond, there is a restriction between the groups attached to the carbon atoms. So, there is no free rotation as present in the saturated hydrocarbon. Two different spatial arrangement of methyl groups about a double bond in 2-butene gives rise to the following geometrical isomerism. So, one is known as cis-2-butene and another is known as trans-2-butene. In the case of cis-2-butene, both the methyl groups are on the one side of the double bond, while in the case of trans-2-butene, both the methyl groups they are little bit opposite around the double bond. So, when both the alkyl groups are present at the one side, then they are known as cis, or when both the groups are on the different opposite to each other around a double bond, then they are known as trans form. So, these are the examples of the isomerism. So, next topic of our today lecture is organic reactions. We have already described described hydrocarbons and looked at their structural isomers. We reviewed how to name hydrocarbons and compounds containing functional groups. Organic compounds have covalent bonding, and generally there is homolytic or heterolytic bond cleavage take place.